Okay, so let us start. So in the last lecture, we started discussing about initialization, right? How to initialize your parameters of the neural network so that uh, it is properly updated. Obviously, we said that it will not help us reach the global optima, but at least what it will help is, for example, it will um, help us in exploring the space probably in a better manner. Um, it will help us in addressing the fact that it will not get stuck because of the saturation or because of dead unit in ReLU. It will help us in ensuring that all weights are not getting updated similar, I mean, in the same manner. So that means which is kind of a constraint and which can potentially stop the network from learning, right? And in that context, we just started talking about designing a good initializer for tan H, tan hyperbolic activation function, although we did not do much, but we at least started. So for today, the plan is we will talk about derive um, the initialization scheme, a good initialization scheme, hopefully for tan hyperbolic activation function. And from there, we'll look into other aspects of other challenges associated with optimizer in the context of deep learning primarily, right? So that is the plan for today. So let us start, right? So today is what, lecture 8, and we are going to we are trying to today to at least answer the question that can we design um, a good initialization scheme when my activation function is tan hyperbolic, right? So how to design a good initialization scheme for tan H activation, right? So this is what we will be mostly talking about today, right? This is what we'll be mostly talking about today. Okay. So from the last lecture, uh, if you remember, we discussed and kind of concluded certain things for designing a good initialization scheme. The first thing, so can you remind me what are the things that we discussed regarding initialization, at least the take home messages from last lecture? So can you remind me? So from last lecture, what are our learnings? So let's say the first one. What was the first learning? We should not initialize at constant or zero value, right? So weights, or I'll write theta, should not be initialized from a constant, and that constant can be 0 or something else, but it should not be constant. What is the problem with that? If you initialize from a constant value, then they will remain constant because your update, the gradients will be same, and because your gradients will be same, it will be theta t plus 1 is equal to theta t minus eta times gradient of loss with respect to gradient of loss evaluated at theta t. So it will remain to, it will continue to be constant. It will not be learning different features, which is the original goal. If you go back to maybe third or fourth lecture, if you remember, we talked about that in neural network, the nonlinear activation help us learning different basis function, right? We had that point of view also. So with a constant initialization, it will be learning the same basis function. It will not learning the features, the different features possible, which is not a good thing. This is one of the things. What else did you discuss, or what were the other messages from last lecture apart from this? It is activation function dependent. So that we already know because we are talking about that for tanh activation function. So it is activation dependent. And the last thing we discussed was that because of this point number 1, maybe it is a good idea to initialize the weights randomly. So weights can be initialized randomly. Now, when I say randomly, it can be any random distribution of your choice, but what we usually prefer is Gaussian or uniform. What I will be restricting our discussion to is Gaussian. But it does not mean you have to use Gaussian. You can also use some, let's say, uniform distribution if you want it to be bounded. Gaussian is unbounded, minus infinite to plus infinite. So one of the choice is weights can be initialized randomly. So one choice is, let's say, theta from Gaussian with some mu and sigma w. Okay. So the second point is weights can be initialized randomly, and that will ensure that they are not initialized at the same point, right? So kind of addresses the first point. In the context of tan hyperbolic, did you discuss anything else? Let's say what should be the mean? 0, because tan hyperbolic is symmetric about I mean, it's symmetric, so mean seems to be a good, 0 seems to be a good choice for mean. It goes from -1 to +1, so in that sense. So let me draw the tan hyperbolic once here. So something like this. So the third thing is that we set mu is equal to 0 because one of the reason I said is symmetric. Other reason is also that if you look into the whole tan hyperbolic graph, near 0, it is kind of linear with a proper gradient. Away from 0, it will potentially give you a saturated unit on both sides, on both positive and negative side. So we set mu because one is gradient is well defined, which also means that it is not saturated, right? It is not saturated, because if it is saturated, then you will end up getting 0 gradient, which means no update, right? So theta should not be initialized from a constant. Last lecture we discussed weights can be initialized randomly. That addresses the first issue. We set mu equal to 0 in this case because gradient is well defined, and also near theta equal to 0, you can see that it is almost linear. So we are going to use that linear approximation as well in our derivation of a good initialization scheme. So it will not only be useful because the gradient is well defined, it will also help us in making the math tractable. So that is another reason. Anything else that we discussed? There is one last thing that we discussed, which was the last point, that if we take a very deep neural network, variance of each layer should ideally be 1. If it is greater than 1, then it will potentially blow up. If it is less than 1, it will go towards 0, which means that insensitive. So no matter what input you are giving, you are getting the same output. And in the other case, blowing up things, even a small change in the input will result in huge change in the output. So if it is greater than 1, it will result in blow up. If it is less than 1, it will be insensitive. So basically, no matter what input you are giving, the output remains the same. So that means you are not learning anything. You are probably memorizing to output one thing in some sense. And that was kind of the last thing we discussed. And this is where we will start today's lecture, or at least the new content for today's lecture. The last point is sigma W needs to be computed, and our philosophy is going to be, I mean, you can come up with another philosophy. I mean, maybe another aspect you can look into, and maybe you can design another way of finding sigma W. But this is a reasonable philosophy that it should not blow up. Okay, so it needs to be computed, and the philosophy is going to be variance of each layer should be as close to 1 as possible. And this is a statement I am giving right now, that variance should be as close as possible as, I mean, as close as possible to 1. This is right now a statement, but soon I will write the expression of variance of one layer, and you will realize that, because ultimately what you want is variance of the last layer to be reasonable, right? What you want is variance of the last layer should be reasonable. Now I will soon write the expression of variance of one of the arbitrary layer, and you will see that it depends on variance of the previous layer. And because of that relation, we are forced to make it close to 1. Otherwise, our objective is variance of the last layer, that is the output layer. The variance of the output should be reasonable enough. It should cover the data distribution. I mean, that should be the original goal. But as you will see, variance of one layer will depend on variance of the previous layer. It will kind of be a recursive relation. And because of that, we will be forced to push it towards 1. Because otherwise it will blow up for a very deep network. And we'll see that. Okay, I'm just giving you some spoilers that is going to happen. Okay. Okay. So now with that, let us start. Okay. So with that, let us start. So let us consider the ith neuron of the jth layer. We started with this last time. Neuron of the jth layer. Sorry, not J, I'll write L. L stands for layer, right? Of the Lth layer. So this is equal to what? H, or first I will write Z. Z Lth layer ith neuron is equal to summation over Lth layer ith neuron is summation over J width of the Lth layer, and it is connecting J to I. So J I times H L minus 1 J. Bias I am taking to be equal to 0. Now this expression I am not going to explain again, but last time we saw that what is happening. Last lecture, I mean towards the end, we saw that how we arrive at this thing. This is basically, if you take one layer, it is dependent on the neurons of the previous layer. So there should be summation over those. That's what the summation sign is doing. Each arrow has a weight sum of its own, which is WLJI, and the hidden units. I mean, that's what we saw last time, right? And along with that, we also wrote this last time, so this is not new. tan hyperbolic of right. This is what we wrote last time. Okay. And along with that, we also know that the weights are sampled from a Gaussian distribution with zero mean variance sigma w squared. Along with that, we also know that weights, any weight, right, is sampled from Gaussian with zero mean sigma w square as my variance, right. These are things we know. Now let us try to compute the variance of H, right. We are interested in computing the variance of H at the initial portion, right, at the initialized weights. So let us see. So taking variance, we get variance of H L I is equal to, now tan H, right, tan H we are talking about, where W, what is the mean of W? 0. And if you look into this plot of tan hyperbolic, we will like to be in the linear zone, right. So if you are in the linear zone with 0 as my mean, I can use a first order approximation. From here I will mostly be let us say in this zone, I don't know, I mean at least that is the idea, I will be in this zone. So if that is the zone I am in, that is like a linear curve. A first order approximation is a reasonable approximation. And what is the first order approximation of tan hyperbolic of z? It is equal to z. So variance of this is equal to variance of tan hyperbolic of ZLI, which is approximately equal to variance of ZLI, right. And now we will work with basically the variance of ZLI. So we will try to compute that variance from the first equation. Okay. So now, which basically implies variance of ZLI is equal to variance of summation over J W L J to I times H J, sorry, H L minus 1 J, right. This is the thing. Keep in mind the model is not yet trained. So we are just initializing. So there is no influence of the training data yet. It just the model is just getting initialized. So we are just setting a random weight to start with. There is still no data into picture. Okay. So if there is no data into picture, right? So now think of a model, right? Let's say the model has x1, x2, x3 as my input, and we assume these features are generally independent. The input features are generally independent. You don't use dependent features, right? So x1, x2, dot 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 xk, if I take, they are generally independent. That's a reasonable approximation, right? Now you are drawing W, each of the W independently from Gaussian. So W's are not drawn dependently, each is sampled independently. So you have an independent random variable, I mean independent input, x1, x2, a sample of that. The samples are anyways IID, features are also independent, and it is getting multiplied with weights that are drawn independently. So this summation will also be independent, right? So which means W times H, so W1 Ij, W1 1 2 H, let's say 1, and W1 WL 1 3 H 1 or something like that. These are all independent. So I'll repeat what I'm saying. What I'm saying is as follows. So the first thing I'm saying is, features input features are independent. This is a reasonable assumption to make. The second one I'm saying is, what is happening? Somehow it is not writing. I don't know. My pen stopped working. Input features are independent. The second thing I am saying is that weights. I don't know how to teach now. It stopped working. Let me try closing it and see. Sorry? Yeah, that's what I'm trying to do. The second thing I was saying is input features are independent. Second is weights. No. Reset the whole device. Let's try that also. Otherwise, we'll have. Let's see. This is not chargeable. This is stylus. You don't charge it. Probably I know what is happening. Somehow this is moving, I can see. Anyone has a Samsung stylus? Whether you have? Let me try that one. That might be the reason. I think this is moving somehow. Let's try this one. Hopefully this will work. Yeah. I don't know, somehow this tip seems to be moving. Okay, let us wait till it gets started. But anyways, yeah, I'll write it once it's done.
The input should be independent, but there are a lot many scenarios are there where you won't have this independent pivot. Then what we should
Then, I mean, generally in most cases they are independent. If they are not, then I mean again, I'm not talking about CNN here right now. This is being talked about a fully connected network. So tabular data. This is not time series data yet. So in tabular data, generally they are independent, but let's assume they are not independent. The easiest solution is to transform them and make them independent. You do a Cholesky decomposition and make them independent, that goes as your input. So if they are not, that you can do. First thing first. Second thing, you will see that after all of this, we will arrive at something, obviously, but in that there will be approximation as well. So it will not be that it is perfect. It will not happen, right? So there is already I have taken one approximation. There will be other approximations that will also be taken. So this will give you a reasonable starting point. It will not be like the perfect initializer. There is nothing perfect in deep learning. Let me put it that way. Okay. First, I'll try my own, and then I'll try the other. This is definitely not working. Yes, stylus problem. Thank you. It should work. Now, this is a new problem coming. So, second thing is, yeah, weights are sampled independently, right? Now, okay, so two things are input features are independent. That's a reasonable assumption. It is responding, I can write. So, why is it saying it is not responding? So, weights are sampled independently and the input features are independent, which means each term inside that, let me close it and open it, right? So, each term inside that summation that you see, they are independent. Okay. Okay. So, because of this 2 points on the right hand side, each term inside the summation is like independent. So, what happens when you have variance of variables that are independent? What is variance of A plus B when A and B are independent? Variance of A plus variance of B. If they are not independent, then covariance comes into picture, but that will be equal to 0. So, because of these factors, we can write it as, so this is equal to summation over J variance of W L J I H L minus 1 J, right? So, one thing that you can immediately notice is that on the right hand side I have variance of H L minus 1, obviously multiplied with W, right? And on the left hand side I have variance of HL. So, clearly the variance is a recursive relation that I was talking about earlier, because Z is basically H, at least in the near the 0. So, the recursive relation of variance does hold. And now we will try to work with one term inside the summation and simplify it and see if we can make some sense out of it. Okay. So, okay, so we consider the term inside the summation. And because I'm going to generalize it, I will drop the L, J, and I, this index. I will only work with variance of WH. Those index will have no meaning right now, so I will just drop it. It does not mean they are not there. They are there. When I substitute it, I'll bring it back. Okay. So what do I have? I have variance of W times H. Right? The index that you see above has been removed just because of, I'm going to simplify it. When I substitute it, I'll bring it back. Now, what is variance of quantity? Variance of a random variable. How to calculate it? Expectation of variance of x is equal to expectation of x square minus expectation x whole square. I mean, this we do in school, right? I mean, the first statistics course. So this is equal to expectation of W square H square, right? Minus expectation square of W H, right? Now, what can you tell about W and H? Are they dependent, independent? And keep in mind this term, the index also, when I'm talking about it. Are W and H dependent, independent? What is it? Independent. Both are drawn independently. I mean, X is independent feature. That's how W coming, and W is also independent. Okay. Yes. WL and HL are not independent because HL is calculated as function of WL, but WL and HL minus 1 are independent. And that is what you are seeing here on the summation. W is L, H is L minus 1. That's why they are independent. But WL and HL or ZL, they are dependent because ZL is a function of WL. If WL changes, ZL will change. But if HL minus 1 changes, WL need not change. Right? So if they are independent, then what is E of AB? E of A into E of B, right? So this is equal to expectation of W square, expectation of H square minus, same thing will hold here, expectation square of W, expectation square of H. Now, what is this term equal to? Expectation of W is 0. That's what we assumed. So this is equal to 0, which means the second term will vanish. It has no role to play. So then this is equal to expectation of W square multiplied by expectation of H square. Let us only take expectation of W square. How can I write it in terms of variance? With variance of W, then plus expectation square of W, right? I mean, same formula that I used here. Same formula, just take the negative side sign to the right hand side. So this is then equal to variance of W plus expectation square of W multiplied by expectation of H square, right? Again, this term is equal to 0, same term, correct? And now what we can do is as follow. Uh, this term, let us take, and I can write this second term in the same formula, variance plus expectation square. So let us do that. So this is equal to variance of h square, sorry, variance of h plus expectation square of h. Okay. Now what is h? Output of hidden unit, right? What is the, how are you calculating the output of hidden unit? Tan hyperbolic of W transpose x, there is no b, right? Now what kind of function is tan hyperbolic? It's an odd function, right? Because it's an odd function, and anyways from the diagram you know that expectation of h is equal to 0. Odd function, the probability on the left and right hand side are equal, which means the expectation of h is equal to 0, and that is also evident from this diagram. It's symmetric about 0, so it's 0. So this term here is equal to 0, and this is because tan h is odd function. Okay. So then what am I getting after this multiplication now? What am I getting? Sigma w square multiplied by variance of h. That's the only term that is surviving, right? So this is equal to sigma w square multiplied by variance of h. Okay. This is the only term that is going to survive. Now, you take this term and substitute it into the summation term, because our goal is to find out variance of HLI, which is equal to variance of ZLI approximately, and that is what we want to find out. So I am going to take this box that you see at the bottom and substitute it inside the summation with proper index. Now the index will come back. So substituting into the original equation, what we get is as follow: variance of h l I, which is approximately equal to variance of z l I, which is equal to summation over j sigma w square variance of h l j minus 1. H l minus 1, right? Sorry, h l minus 1 and then j. Sorry, the minus 1 is at the bottom. This one, right? Everyone follows? Now, what is variance of L minus 1 times j? There is going to be one more assumption in some sense I am going to take. I am going to make it equal to, so this term, right? This is variance of one neuron in the L minus 1th layer. It is variance of the jth neuron in the L minus 1th layer. That's what it is, right? Now what, and it is recursive, by the way. Now what we are going to do is that now you can see that if, and there is a summation there, right? If this is more than 1, you can see what will happen here. So that means each of this term is supposed to be as close as to 1 as possible. Ideally they are supposed to be all 1, right? Each of the unit, the variance, I want it to be close to 1 so that it does not blow up. So what I'm going to do is that following our original target, variance of h L minus 1j should be equal to 1, and it has been set when I was in variance of h L minus 2, because we are starting from variance of x, the input one, then h1. So h1 is set, then I will go to h2, then h2 is set, then I will go to h3. So because it is a recursive relation, at L minus 1 I am going to assume that it has been already been set, is achieved in the previous recursion. Following our original target, variance of this has been achieved in the previous recursion. I mean the recursive formula goes, right? And this is for, by the way, all j. Any question on this part? This is clear what I am doing here? If that is the case, then what is this equal to now? So which implies variance of HLI is approximately equal to N in times sigma W square. What is N in? Number of neurons in the previous layer. I am calling it N in because it is N input. So for that layer, that is the input. Okay, but it is basically the number of neurons in the L minus 1th layer, right? And now what do we want? I mean, and now target is where HLI equal to 1. This is our target. Now at this layer I need to establish this. Previous layer was recursively achieved, but now I have to ensure this for the current layer. What does it mean? Sigma W squared is equal to 1 by. So if I set this value, then it ensures that during the forward pass, the variance will not blow up, it will be 1, right? If I set this value, it will ensure that during the forward pass, okay, the variance will not blow up and it will be reasonable enough. But is that enough? Do you think only setting the variance in the forward pass is enough? Generally the answer is no. You also want to look into the variance during the backward pass. It can also blow up because the variance, I mean the gradient, the variance of the gradient becomes very high. And that can also make your learning problem chaotic in some sense, right? So then if that is the case, we should additionally satisfy that the variance does not blow up even during the backward pass. So we also want to ensure that variance does not blow up during backward pass. Now, I am not going to show this calculation, you can do it on your own. But what do you think it is going to give us? Because now the variance will be calculated from the other side, right? So, what do you, because back propagation, chain rule. So, what do you think it will give us? So intuitively, it will give 1 by n out. Because if in this direction the input was nn, so it was giving 1 by nn. When I'm returning the input in back propagation is actually n out. So this is going to give n out. You should derive it on your own, same process, same kind of assumptions or approximations, same thing you will get. Okay. This gives us sigma w square is equal to 1 by n out. Now both of these can it be satisfied simultaneously? Only if n is equal to n out, which is like each hidden layer has the same kind number of neuron, which is a very restrictive, I will say, architecture. You will not want that to be enforced. So you cannot do that. Okay. In a generic sense, n will in will be not equal to n out. And it's not about reaching up close to a value, it's about 1. Less than is also bad, greater than is also bad. So a reasonable approximation that was proposed was to do the harmonic mean of these two things. So considering forward and backward pass, we set sigma w square is equal to 2 by n in plus n out. And this is set at each layer. At each layer, you set the sigma in this manner. By the way, this was not done by me, obviously. This has a name. This is known as the Xavier's initialization. This is known as the Xavier's initialization. Okay. There are other choices also. Harmonic mean, it does not, I mean, you know, arithmetic mean less than equal to geometric mean less than equal to harmonic mean. So from there, out of the 3 mean, you take this one. So that in that sense, that the variation is less in that sense. But again, at the end of the day, as I was saying earlier, right, this is not perfect. But this is the most reasonable thing that exists, as long as you are dealing with the tan hyperbolic activation function. And this is again derived only for tan hyperbolic activation function. You are using, let's say, ReLU activation, then you need to, there is other initialization that is optimal for ReLU activation function. Okay. I think Zamming is the name, Zamming Hay or something like that, that is used for ReLU activation function. Again, I'm not doing ReLU activation function, you should do it on your own, but you will realize that there is nothing perfect. There are certain assumptions and approximation, and what is the best you can do is the question. Make sense? Okay. So ultimately, how will you initialize? So ultimately, weights are following. Xavier's initialization was from Gaussian 0 comma sigma w square, where sigma w square is equal to 2 by n in plus n out. Okay. So, this is the thing that you will need to actually work with tan hyperbolic activation function and start your training. Remember, this is the starting of the training. Obviously, after training, things will get changed and all of those things. Any question? Okay, so it took me what, 40 minutes? I was hoping to do it last lecture. Obviously, I was nowhere near, definitely. Yeah, anyways, okay. So the other initialization schemes, for example, the ReLU one, you should practice on your own. Maybe I will give it in the homework, but that is to be practiced, okay. And similarly, for new activation, you might want to derive it and see if you can derive something for, let's say, the newer activation functions, GELU, MIS, and I think CILU is also there, CILU. So those kind of things you can try that if you can find a good optimizer, a good initial guess. If you can, that's a good work. Okay. Okay, so we are done with initialization. The message that you should take from the discussion on initialization is that the mean needs to be set properly. The variance needs to be determined based on the activation function you are using. Even the mean is based on that. So it is activation function dependent, as we discussed last time. You should avoid the saturation or dead unit, I mean dead and saturation zone. That needs to be avoided to the extent possible. And last but not the least, you should definitely remember this will not guarantee you global optima. Nothing guarantees you global optima. So you are still going to get local optima, but hopefully a better local optima. Okay. So that these are the yeah, these are the this is all that I wanted to discuss on the initialization part. Any question on the initialization part? If not, I will proceed with other discussions, other concepts in optimization. Optimization is not yet done. Definitely, we have not gone to other advanced optimizer. We are only talking about gradient descent variants till now. So advanced ones will also come, but even within gradient descent, we are not yet done. So any question on this part?
So why do we have our target variance as 1? Is it because we want the output to have less variance?
No.
with respect to different?
No. Think about it. Your variance is coming in this form, right? Where is that? This one, right? What I said to be equal to 1. See, now imagine a layer, and there are neural networks actually. So imagine a neural network that has, let's say, 150 layers. Okay. Now the way you are calculating it is that it's a composition of function. So HL depends on HL minus 1, which depends on HL minus 2, and so on and so forth. Correct? With that in mind, if you do not set it equal to 1 because of this 150, which is a very big number, even a uh, even a let's say less than 1, let's say 0.9, it will get 0.9 to, it will become 0.9 to the power 150. So the variance will become very small. What does variance very small mean? That means the output is now deterministic. If the output is deterministic, no matter what input I am getting, I am getting the same output. So I am not learning anything. This is on the smaller side of thing. Now I assume it is 1.5, greater than 1. Same thing, 1.5 times 150. So it will become a very big number, which means even my input is getting changed by 0.1, the output will be hugely different from one another, which is the ideal case for chaotic dynamical system. In chaotic system, it happens. Even if the initial condition change a little bit, the output varies a lot, which means it is now blowing up. So either of these you do not want. at the beginning. At the beginning, you want things to be stable. Now, this one, will it stay? No, it will not stay. It will stay only at the beginning because that's a stable point to start your training. And now it is possible, right, that all your data point is giving the same input, output. Then let the network learn from the data that I should adjust my weight in such a manner so that the variance shrink. Or let the weight learn from the data that I should adjust myself in such a way such that the output has a huge distribution. So that part it can still learn, but it will learn. You should not initialize that it is very large. Because then if it is small, it will not be able to come back to that. Because the gradients will be ill posed and all of those things will come, right?
So we did this because of output variance.
Correct. We did it because at the beginning we don't want our output variance to blow up or shrink. Because of that one, right? Any other question? If not, let us proceed. Yeah. Yes, because W's will change, right? Now, while learning, W's are not now known. In fact, once you start learning, W's get dependent because they are now conditioned on the same data. So conditionally, they might be in the. There is some conditional dependence that comes into picture now, right? So that now the weights will not be severely initialized. So as soon as it is not Xavier initialized, it's not Gaussian any longer. So then nothing will hold. This is only for the beginning. At the beginning, you don't want things to blow up or be too strict. It's like, it's not exactly, but you can think of it like bias variance trade-off. Going towards zero is like bias, right? So highly biased. The variance is like too big. So you can think of it even from the lens of bias variance trade-off. Again, that's an analogy, not exactly, but you can think of it like an analogy in that sense. Right? Any other question? If not, let us move ahead and let us try talking about what other problem you can potentially face in optimization for deep learning, right? If there is any other problems that needs our attention. So, okay. So, what we are going to talk about is basically ill condition. Okay. And for this part, I am going to talk about, I'm going to go back and take an example from the linear regression. Okay. Because convex optimization is always easy to explain, easy to follow. Okay. So consider y is equal to w1 x1 w2 x2, and there can be a plus b also, but yeah, there is a plus b also. Let's write that also. Okay, but we will only focus on w1. Okay, and now suppose that the x1 varies from 0 to 5,000. So the data points of x are quite high, 0 to 5,000, but most of the data are 1,000, 2,000, 3,000, 500. So x1 varies, has a larger range to vary. Okay. So what we are going to do is that x1 varies between, let's say, 0 to 5,000, and 5,000 I'm just taking as a random number. You should imagine it to be a large number. Okay. Okay. And similarly, let us assume that x2 varies between 0 and 0.1. That means x2 has a very small influence. Okay. Now, with such a data, if you train this model, And don't think of a special case where one is independent or something like that. In a generic sense, I'm talking about both are equally important or something like that. So if you train train a model, which is the linear regression model, with such a data, what do you think will be the characteristics of W1 and W2? What do you think will be the characteristics of W1 and W2? W1 will be very less. W2 will be very high. So if this is the data set, this potentially in a generic sense, again, there can be special cases also, but in a generic sense will result in W2 much greater than W1. This is what you will get, right? And now with this W2 and W1, where W2 is much greater than W1, okay? If you plot the loss landscape, in this scenario, the loss landscape will be something like this, okay? I mean, not exactly, but okay. Right? The loss landscape will be something like this. Where the gradient, if you look into the gradient with respect to W1 will be quite high, whereas gradient with respect to W2 will be quite low, right? This is what will happen. You will get a loss landscape like this. And keep in mind, gradient with respect to W2 is quite, W2 with respect to that is quite low, right? Gradient with respect to W1 is quite high. So basically my y-axis is W1, x-axis is W2. Okay, correct? So in that case, what will happen? How do you think it will behave if I start from some point here? I start from here and this is my optima. How do you think it will, do you think it will move? How does anything move? Theta t plus 1 is equal to theta t minus eta times gradient, right? Now you have two gradient here. So how will it move? In which direction it will move fast? The direction in which the gradient is more, which is this direction. The gradient is more in this direction. So it will move something like this. Something like this, right? Is this a good convergence? Not at all. It should have moved more in the other direction. A good convergence would have been something like this, right? The best convergence. Instead of that, because of this gradient, it is going up and down. This is known as ill conditioning. This is ill conditioned because the data is not in the same range. And because the data is not in the same range, W is in a different range. Because W is in different range, the gradient of one is more, one is less. So when you use theta t plus 1 is equal to theta t minus eta, and eta is same by the way for both cases, gradient of these two things, one goes very sharply, one goes very slowly. So basically if I write like this, right? So W1 t plus 1, W2 t plus 1 is equal to W1t, W2t minus eta times gradient with respect to W1 L WT and gradient with respect to W2 L WT. This is my update rule, right, in vector form. Now what is happening? See, let's say you have initialized to both the values at with some good initializer, which is the starting point, right, leftmost. Now here W1 and W2 is your previous guess. That does not matter. What eta is same. So eta will not change based on W1 or W2. But now look at the gradient term. One is quite high, one is quite low. So in one direction it will move very fast, in one direction it will move very slow. Right? But the direction in which it is moving faster, that is not the direction I will reach my optima. Because it is skewed, it should have moved more in the other direction. And that is basically what ill conditioning is. So such kind of behavior you can find when your data is not centered, when your data is not in similar kind of range. You follow what the potential problem is? So what is the solution? Normalize. So one solution is normalization. To address this, we normalize. Okay, which is basically standardized. Basically, mostly we do standardize. So what we do is x minus mu by sigma is what we do. Basically, convert it into a zero mean unit variance kind of thing. And with this, if I use this formula on the data sets x1 and x2, both will be zero mean unit variance, same kind of range. W will be in same kind of range. So this diagram will now be, after normalization, this diagram will be a proper Gaussian distribution. So something like this, right? And as a result, now both are equal kind of gradient. So in both direction, it will move equally. Make sense? Now this was linear regression. In a neural network, you will have multiple such units. This was calculation 1 unit, right? So in neural network, you have this kind of behavior in each neuron. And that is why there is this concept of batch normalization, where inside each neuron, after you compute, you normalize it. So in neural network, we normalize each. In neural network, we normalize each neuron. Okay, before in each neuron output, let's call it, before passing it to the activation, passing it to the activation. So basically you will do Wx plus b, that is your z, you will normalize z and then pass it to, let's say, tan hyperbolic or ReLU or whatever. So batch normalization is generally used after the pre-activation and before the activation, because your activation is already kind of well posed. So that so if you normalize the linear part, activation outputs will also be reasonably normalized.
Why do you batch?
Because you do for each batch of data. How will you get the mu and sigma? I mean, you know the mu and sigma, let's say, of your whole data at the input layer. But at the H level, how do you know mu and sigma? So this is done for each batch.
So we are doing normalization and the pre-activation.
After the pre-activation.
After the pre-activation.
Yes.
And individually for every neuron.
Yeah, exactly.
So how do we know the mean and variance?
You don't know. So that's why batch normalization. So that means you pass one batch of data during training, right? For that you get your H or Z. From there you calculate your mean and variance, do it, then pass it through activation. So because you will not know.
So the first pass is to get mean and variance.
No, every time you will have to do it. I mean, it will not pass all data and get it. You will pass data as it is and normalize it. Because weights are getting changed, so the normalization will change every time. So during training, every step will do that.
But why not standardize the data?
Why not standardize? Then you are passing the whole data. Anyways, it will slow things up. So in that sense, right? I mean, the whole idea is that you will not, we don't have the capacity and memory and RAM to pass all data. That is the big assumption to start with.
So we have already done the normalization on the data itself. It is near to that,
but W is not. W is during training. W might still be something like that, right?
where we don't do
And that is not in our control.
we,
So remember that because of the neuron thing, right? We did on X because it was single layer. Now when you go to the third layer, the input is the second layer. Now in second layer, what has happened is not in our control. And the batch norm layer, the computing gradient is not that expensive. So you just add it. Okay. This is called batch normalization. Okay. So basically, if I look into the code, I will not write a whole code. So but first you will calculate Z, and then you will apply batch norm. And then you apply activation. By the way, this is now, since you are doing this, right? This, so one reason that tan hyperbolic was proposed, instead of sigmoid was that it was zero centered. So when you do this and apply the activation, if it is sigmoid, your data is not zero centered. And we prefer to have our data zero centered. Tan hyperbolic addresses, that is. So it was at this stage when these developments were happening that tan hyperbolic was proposed as an alternative to sigmoid. It has all the properties of sigmoid, but it is centered at 0. So x minus mu by sigma centers your data at 0. So after activation, if I use sigmoid, it will not be centered at 0. It will center at somewhere 0.5. But if I use tan activation, tan hyperbolic activation, then it is centered around 0. So that is one of the advantages. So tan hyperbolic at this stage helps, or ensures is probably the correct term, ensures that the output is centered at 0. Okay. Okay. So to end today's lecture, let us summarize what we have discussed till now. So next lecture will be the last lecture on optimization, where we will talk about the advanced algorithms like ADAM, ADAGRAD, RMS prop, momentum based gradient descent, and Nestrov accelerated gradient descent. So these are the 5 algorithms we'll talk next time, which are all improvements over gradient descent. But before we go there, let us try to summarize what we have discussed till now through a table maybe. So let us see. So we talked about we are talking about optimization in deep learning. And what are the problems we discussed? How do you diagnose those problems? And what are the possible remedies? Let us try to summarize. Okay. So problems or challenges, how to diagnose, and what are the remedies. So what is the first challenge that we discussed in optimization? First challenge. I talked about it today also. The biggest problem, non-convexity. challenges is finding global optima, right, or getting started mid. So non-convexity. Convexity, and in fact the proper terminology is probably in this case local minima. How do you diagnose? You don't diagnose. It's very hard, almost impossible. So you know that you are at local optima. I mean, it's more like that. It's not, you don't even need to diagnose. It's an fact almost, right? So diagnose, there is no other way. So you say hard. What are the remedy? One remedy we talked about. What is the remedy? Multiple restart. So because you're sampling from this Gaussian, right? Do multiple sample, run it and see, and you hope, right? Multiple restart. Okay, this is the first one. What is the second challenge we talked about? Initialization is a solution, maybe. What was the problem? That did weights are same. So, um, so basically symmetry is the problem. You call it permutation invariance of symmetry. Okay. Why is symmetry a problem? Because if you make the network is already symmetric. If you initialize it symmetrically, then it will always remain same. So you need to break that symmetry by initializing separately. Okay. How to diagnose it? Look at the weights in a layer. Basically, look at the weights that will help you diagnose. So check weights, because weights should in a layer, it should not be initialized same. So that will help you break the symmetry. And what is the remedy? Initialization. So initialize it, and that helps you escape this trap. Right? What is the third challenge we discussed about? That is the fourth one. That is correct, but that I will write it at the end, because that is motivation for the next lecture also. So correct, high variance or ill conditioning, right? That is correct, but before that there is one more. Saturated or dead unit, right? And dead unit. How do you diagnose it? Histogram of the neuron output. Because for example, if you are getting very high value as the output of a neuron, then you know it's already, and that neuron and that activation is tan hyperbolic or sigmoid, you know it's a saturated. If you are getting zeros, all zeros, then you know it's dead unit. So the diagnosis is plot histogram of uh, neuron outputs. What is the solution? Initialization is the solution for this as well. Also, you avoid the two zones, right? So initialization is the solution, but along with that, initialization normally does that, so I'm not writing it. And the last one is obviously data is ill conditioning. The data is ill conditioned. How do you check it? Again, it is very hard to check it, but because at each layer you have so many layers, at each layer you have to say, because you don't know. The data might be ill conditioned at the beginning, you are thinking X, but it might be ill conditioned at some H in between also. You need to check all those neurons. So it is generally hard. You can do it by checking each neuron. So hard, but can be done by checking
data level you can check.
But even if the data is balanced and you are not doing batch normalization in each layer, in between it might happen. Let's say you are using a ReLU activation. Data is balanced, but in the training process, and in between, at some stage, because of the ReLU activation, it become ill conditioned. So I'm not only talking about data in ill conditioning, but ill conditioning as a whole. Each neuron at each iteration. And clearly, if you have to check each neuron at each iteration, it's hard. Solution, one of the solution we said is batch norm. There are other solutions we'll talk about, which is basically momentum, keep bringing momentum into picture, bringing developing, I mean, using better algorithm, using ADA, grad, ADAM, all of those things. And so other areas are, and this we have not yet discussed, so this we will discuss next time. Advanced optimization algorithms. So this green one is the only thing that is remaining in this part, which we'll discuss in our next lecture, right? And then we'll go to generalization, and after that CNN. So generalization will spend some time, but yeah, maybe 2-3 lectures, and then we'll go to CNN. My hope is before midterm, minor is what we call it here. So we'll be done with CNN. So that after minor, we can start with the sequence learning, and in 2 or 3 lectures, we can get done with the main sequence and learning, I mean, the basic sequence learning algorithms, RNN, LSTM, and GRU, and then we can start with transformer. So that is basically the plan. So pre-minor, we want to finish up to CNNs. Post-minor, 3-4 lectures, maybe 2 lectures, get done with the RNNs and LSTM stuff, and start with transformer. So that is more or less the plan. Okay. Any question? Otherwise, we are done.
So in some scenarios, we also use the layer normalization and batch norm. So when do we know that which one?
You don't know. You just look at it and try things out. Mostly hyperparameter. Yes. Okay. Thank you.
Can you scroll to the top? Some 2 lines are missing.
Hmm?
Some 2 lines are missing. So can you scroll to the top?
Here. Okay.
To the very top.
Okay. Okay. Thank you.